I'm extremely excited to present my PhD defense in a research talk titled Safe Planning Under Uncertainty Using Surrogate Models. Now, to break down the title a bit, what I mean by planning here is taking a sequence of actions or sequential decision making for autonomous systems or decision support tools. This could be vehicles both on the road or in the air. This could be robotics. So a lot of the work we do is applied to robotics domains, as well as this could be decision support tools for geological problems that use machinery to, say, drill to understand what's underground. But the important part about planning is the sequence of actions. So we're taking a sequence of decisions in some environment as opposed to just a single decision. Now, we want to plan under uncertainty, which makes this a little bit more challenging. So we want to operate in a realistic environment where there's sensor noise, so we have some uncertainty about the state of the world, as well as stochastic or random dynamics as the agent moves through the environment. But what's important here is that we want to do safe planning under uncertainty. So we want to take safe actions given some target level of safety. We want to avoid these unsafe states. This work studies the use of surrogate models as a way to replace the true system or some heuristic with a low-dimensional approximation, here say a neural network as a surrogate, in order to run validation or planning more efficiently over this lower dimensional surrogate model. So safe planning has been in the news a lot recently. Autonomous systems are becoming increasingly popular in our present lives or everyday lives, especially here in California, where self-driving cars are everywhere. Yet these vehicles still pose some safety risk that we must study. Other domains, such as, say, fighting wildfires from the air, may benefit from some increased autonomy in order to remove pilots from these dangerous situations, as you see on the right here. Now, recent companies such as X-Wing, which is now part of Joby Aviation, where I worked a couple summers ago, they've paved a way for fully autonomous flight as a potential way to open new avenues for where autonomy could be useful. Yet, as we can see with the recent mid-air collision back in January, safety critical systems are not the silver bullet to remove all risk, but are incredibly important to study. Autonomous systems have also found new and important areas in which to plan, including autonomous rovers that traverse the lunar surface in order to drill and search for ice deposits on the moon in hopes of finding water on the moon. And then finally, back here on Earth, researchers are exploring how to offset CO2 emissions and have turned to sequential decision making in order to make decisions for where to drill to safely sequester CO2 underground. Yet these systems still need improvement, as a recent CO2 sequestration plant in the US leaked CO2 into a local drinking water source. So all this leads to my research question, which is how can low-dimensional surrogate models be used to enable high-dimensional planning in safety-critical systems? Now, this talk has 4 main contributions going into my thesis that are split into 2 different sections. The first is planning, and the second is safety. So for planning, I'll introduce a belief updater that we can learn for high-dimensional observation spaces. And then I'll introduce a general algorithm for solving long-horizon, high-dimensional POMDP planning problems. And then I'll extend that work to the safe planning domain, where we can learn safe policies given some target level of safety. And then lastly, once we're given a safe policy, we want to estimate the probability of failure for that policy. And so I'll introduce an algorithm that uses probabilistic surrogate models to efficiently estimate that probability of failure. So all this work is pretty general, and it's applied across very different, seemingly unrelated domains. First and foremost is aviation. So I apply this work to aircraft collision avoidance systems, also to runway detection systems, and then finally airborne wildfire suppression systems. So you'll see an example of each of these during this talk. Also, the field of robotics, as mentioned before, we study robot localization and navigation, as well as robot exploration. And then finally, and more recently, the world of geological sustainability and how can we apply safety critical algorithms to these problems, such as critical mineral exploration, safe carbon capture and storage, as well as a geothermal energy production, but I'll save that last one for another time. So you might be asking, how do all of these systems, how do all these problems relate? So all of them start from some state in the world at time t. And as a running example, we'll talk about, say, autonomous driving, where the state of the world could be, say, some XY position of the vehicle. And there's also, say, an obstacle we're trying to avoid that also has some XY position that's part of the environment. So we call that the state. The goal would be to take some action. In this case, say we want to avoid this obstacle, and we would get some reward for taking this particular action to avoid it. We could also take a different action and say, do nothing, and this would have a small penalty because it's a cone, we would hit it, or you could have a large penalty if you veer off the road. So once we take that action, we use a transition model, which transitions from our current state, given an action, to a new state at time t+1. And then we could continue this into the future for another action, you get another reward, and this would expand. And this is called a Markov decision process, or an MDP. And now, of course, you can continue this to more time steps in the future, and you can see that this is why it's difficult to plan over sequential decision-making problems because of this exponential expansion of the possible features you could take. What's even harder is the fact that states are unobservable in real-world problems. So I don't know the exact XY position of a vehicle, but what we can do is get something like an observation or a measurement of where we think that vehicle is. So instead of seeing the exact position, we can get something like, say, GPS measurements or some sensor measurements. This is called a partially observable markup decision process, where now we have an observation model that tells us how our observations are likely to occur given our current state in action. In POMDPs, we have this thing called a belief, which encodes our uncertainty in the state. So the idea is if we don't know exactly where we are, we have some distribution of where we think we could be. So this could be some fuzzy understanding of where the vehicle could be. We could get some observations from, say, a GPS sensor, and then we could update our belief to fit to those observations. And then we can plan based on that belief. So the goal would be to take the best action given any of the beliefs that you would see here, or any beliefs that we could possibly be in. And the solution for POMDPs is to find a policy pi that maps beliefs to actions A. The objective of the problems would be you would maximize the expected discounted future rewards. And after you get this policy that maximizes this equation here, you would then start from some initial belief. You would take an action from that policy, you get an observation, and you'd update that belief. And then you take another action, you get another observation, you update that belief. So this now leads into my first contribution, which is how can we learn efficient belief updates from partial data? So this is ongoing work that's in submission to the Journal of Machine Learning Research. So the real-world problem that we'll study in this section is subsurface intrusion discovery using muon tomography, which is a mouthful. Here, just what's underground. So say if there's some 3D intrusion or 3D rock that we want to understand, what exactly is underground or in the subsurface, we could take slices of this to look at what's underground. But really the question we have now is where do we drill? So we could drill in any number of these locations. This is showing the top surface. And we have multiple objectives. First is we want to maximize the subsurface information gain. So each drill, we want to get as much information out of it because we want to minimize the number of drills or the cost to drill because we don't want to just drill everywhere in this plot of land. With the final objective for this problem of making a go, no-go decision if the intrusion volume is above some economic threshold. And we use muon tomography as a way to observe what's underground here. And you can see this is just that top slice where the muon observations are slightly skewed because of the angle of these drills. You might be questioning, okay, what are muons? Well, muons are cosmic rays that have been recently used to understand the internal structure of the Great Pyramids better. The idea is that muons are just passive rays that we get from just existing in the cosmos that are only partially absorbed by stone. The way this translates to our problem is if this is our intrusion and we have some drill that goes right through the center here, if we look at each of these yellow dots, these are muon sensors. So we can sense the difference in density of the muons as they passively pass through these sensors to understand what's the density of the rock around it. So we can frame this problem as a POMDP, but one of the research challenges that we try to address is how do we go from muon observations to the true intrusion state or a distribution over true intrusion states. This is through a process called inversion. But what's even more challenging for this case is how do we go from partial muon observations to the true intrusion state? So existing work on inversion methods include particle filtering, which does require an observation model likelihood in order to weight each of the state particles, which may not be available and it may be actually expensive to learn. There are other methods in deterministic inversion that just map a set of observations directly to a single state deterministically. This may not be able to scale well to our problems where we want a distribution or some uncertainty in the state where those observations map to. And often those cases require the full set of observations and they're not robust to partial observations. And then finally, for more probabilistic approaches, they're expensive to sample, often using MCMC to get posterior samples. So a recent survey by Lee et al. Highlighted a need for efficient probabilistic geological inversion methods. So if I showed you this photo and told you, what do you think is underneath this photo? Like, what are these pixels hiding? To the computer scientists or the grad students in the room, you might be able to guess what's under here because they have some prior knowledge that the rest of the audience might not. If I then show you a set of prior shapes that could exist under here, you might be able to tell, okay, it's probably a digit, and it might be, say, like a 6 or an 8. In this particular case, it's a 6. So the idea is if I give you some prior knowledge, you can learn from it to try to understand what could be hidden from this particular set of observations. So the way we'd like to do this is if we have our state and observation, we want to map to some low dimensional latent space that is shared between the two. So we can map the state to this low dimensional space. We can map the observations hopefully close to that state in the low dimensional space, and then be able to use just the observations to sample new states that are conditioned on observations, meaning that they're consistent with those observations. You can see most of these are sixes. Yes, there's an eight that's stuck in there because it might be able to fit here. And then we can do things like take the mean or something to make decisions off this as our belief. The way we do this is by introducing what's called an inversion variational autoencoder. This is a way for our case where we say we start with some state. We run it through a standard variational autoencoder, where this allows us to then sample a reconstructed state. But of course, for our problem, we're worried about having a set of observations and more importantly, a set of partial observations. So we can pass this through an observation encoder that encodes to a similar latent space. And then we can use this during inference to sample states as mentioned before, and then get things like this, say the mean and variance of those state samples. The insight from this particular architecture that we introduce is that we use states and observations during training when you actually have access to true states of the world, and we only use observations during POMDP runtime because this is actually more realistic where you do not have access to the true states in the real world. And we do this through a clever loss function where there's the standard reconstruction loss is as you would see in variational autoencoders. And here we modify the KL divergence. And to explain a little bit of what that's doing is we have a KL divergence that's trying to minimize the divergence between two distributions. Here it's the distribution over that latent space given your state and the distribution over the latent space given the observation. What we mean here is so we want to minimize this divergence so these distributions start to overlap. And then once we pass in an observation, we would hope that that maps close to the latent space for where that state mapped that generated that observation. Then what we can do is then decode this back into the state space to sample states that are conditioned on those observations. We can do this in another area of the latent space to get conditioned samples from our posterior in the state space. The nice thing about this is all likelihood free. So this means we only need our states and observations during training time, and we don't need some observation model during inference. So now the question is, how do we use this I-VAE belief updater during planning? In standard belief state planning, in this case, say one step look ahead, from a specific belief, you would take an action, you would update that belief, and every yellow line here is showing a time when you would call that belief updater. Here we have a neural network belief updater. For those keen in the audience, you might be able to tell, we could speed up this process by just trying to, say, batch those belief updates all at once. So if we have a batched transition model and observation model, then now we have a batched way to do belief updates. We can actually just do with just a single forward pass through all these networks, do for n actions, k beliefs, and m states in each belief, we can do just one giant tensor pass through a neural network. The nice thing about this is if we compare against sequential scaling, just as we did before, where this plot is shown on a log scale of the runtime over the number of batch sizes, we can see that if we instead use batching over the GPU, we get a significant performance increase as shown here. To show you some results, after we've trained a network, if we just pass in no observations, we would get an initial belief of what we think is underground that would look like this. This is sampling 900 states that are consistent with no observations. And what this means is this is just using the prior states that we've trained on. Here we have 1,800 training states that were generated by a geologist who had expert knowledge about the particular problem. And we have 200 testing states that we hold out. And the idea is that without any observations, this is what your initial belief would be. Now to look at some qualitative results. If you look on the left, we can see that the belief over time is converging to the true state, which is shown on the right. Another way to look at this is if we then look at the distribution of economic volume, we can see that the distribution of the belief is converging towards the true volume itself. To show you, if we took all the drill actions, what the error in our belief would be over time. We try out different policies. Here would be like a vertical sweeping policy, which would be standard in geological problems. We also try out a just random policy, which does a little bit better for this particular problem. We introduce just a very simple heuristic policy that will try out all the drill actions, so all 100, and we'll pick the one with the maximal information gain, just using the difference in entropy. You might think that the heuristic and the random policies look very similar, and at first glance they kind of do. But if we look instead at the heat map of the actions that were taken, we can see that the heuristic policy will choose actions that are around the edges of the shape in order to differentiate shapes from one another, whereas the random policy will take actions uniformly random across this space. Another way to compare is that if we implement, say, an oracle policy, which has access to truth, which otherwise we wouldn't have in the real world, we can see that this particular policy is very similar to the heuristic when we look at the heat map shown here. This heat map shows that the oracle and the heuristic are picking actions that have the maximum information around the edges. We also then test against a different belief updater, in this case, a particle filter, which we can see that the particle filter suffers from particle depletion or belief collapse after it has the full set of 100 observations. The I-VAE consistently reduces the belief uncertainty over time, and the heuristic performs similarly to the oracle. So this would be in the case of taking all 100 drill actions, but as I mentioned before, we want to minimize the number of drill actions while also maximizing our information. So say now if we make a decision based on when to drill, if our probability that we think we're in the go or no-go section of our economic volume, we can see that the heuristic has extremely high accuracy in that decision, where it's calibrated so that if you just make a random choice of go, no-go, it would be 50% accurate. We can see we have high accuracy with a small number of drills, so we're still doing that nice balance of decision accuracy without drilling everywhere, and relatively fast in terms of compute for runtime. And so what this means is that this heuristic-based policy with our I-VAE belief updater is an accurate and efficient planner in this specific muon tomography POMDP. Which leads me to my second contribution, which is, can we replace these handcrafted heuristics with a generalizable method for long horizon problems? And this is work that was published last year in the Reinforcement Learning Journal. So the prior work on long horizon planning uses state-of-the-art POMDP solvers like POMC-POW and AdaOps, and they rely heavily on heuristics to scale to long horizon problems. These would be heuristics for value estimation or action selection, which I'll get to, as well as heuristics for upper and lower bounds on the value function. What this means is that there's a research gap in the question of how can we learn surrogates to replace these domain-specific heuristics. To motivate this problem, just as before, if we have, say, an exhaustive tree search where we expand on all actions, in this case, just 2 actions, and we expand on 2 beliefs, you can see how quickly this expands exponentially the further we plan into the future. So we have 2 goals in order to try to reduce planning time and enable long horizon planning. The first goal would be to reduce the breadth of the search, meaning we don't want to try out all actions, but we want to try out promising actions. And the other case would be to reduce the depth of the search. We don't want to plan too far into the future, but we still want to get some understanding of how good the future would be if we continued to plan. So inspired by recent advancements of AlphaZero, we can combine these 2 goals to reduce both breadth and depth using offline neural network surrogates. And the idea is, once we have a trained surrogate that tells us where promising actions are to expand on and what the value of the future would be at the leaf nodes, we can effectively online prune out these cases so we don't actually have to try them in tree search and just focus on informative actions and a really good estimate of what the future would be. So the way we do this is we can represent our belief and adapt this to POMDPs. We have some simple summary statistics as input into a neural network. And the neural network will predict the policy, which is a distribution over actions given that belief, and the value, which is just a real number that tells you what's the value of that particular belief. There are other approaches to how you could represent beliefs as input to this neural network, including the latent belief that we showed in the previous section. We could use that directly as input. You could learn the belief through experience using algorithms like Forbes, or we could add an order invariant layer into the network to actually input the state particles themselves, but we'll leave that for future work. The algorithm that we propose in this section is an extension to AlphaZero for belief state planning. So we call it BetaZero. It's a policy iteration algorithm that uses these learned approximations. The way it works is you have some initial network, as I just mentioned before, that predicts the distribution over actions and the value. You then run n parallel Monte Carlo tree search simulations or MCTS simulations, and this evaluates the current policy. MCTS has 4 stages. The first stage would be selection. So you start from some belief and you want to do some online planning. You would want to select an action to expand on. So we can use progressive widening because if we have a large action space, we want to limit the number of actions we expand on. And we can select new actions from the policy head, meaning these are promising actions that the policy suggests are good. And this shows an ablation of with or without the sampling actions from the policy network and instead sampling randomly from the action space itself. And even in the case here where we have 3 actions, it's still important to actually prioritize what actions you're expanding on in terms of learning here. So once we have that, then we would select an action that maximizes this balance between exploitation and exploration, where we weigh our exploration by the policy head of the neural network. We then take that action and expand to a new belief. Because this, again, is using belief state planning, beliefs are continuous, so we have to apply progressive widening yet again. Then we can update our belief and predict what the future would be by either running expensive rollouts, or in this case, we could use an estimator, or the value estimator, to estimate what the future value would be, and then back propagate that Q value up the tree. We'd run this many times and do that, say, n parallel versions of that simulation. We would collect data on the belief at time t, the tree policy, and the returns, and those would be used to then retrain the neural network, and we would rerun policy evaluation, and then this loop repeats, and this is the policy iteration loop. So once we have a surrogate that we've trained offline, we can then use the same Monte Carlo tree search online with this now trained surrogate and do it much more efficiently. For our particular case, the research gap that we have identified is how do we handle a limited tree search budget in practice, because belief state planning can be expensive. Belief state planning is good because you can plan directly over the uncertainty in the reachable futures, but at the expense of computation, where this might limit the tree search budget in practice because you're doing a belief update at every node. So one way we address this is by introducing a change in the way we imitate the tree policy. In AlphaZero, they use the visit counts, so how many times we visited particular nodes, as a way to try to imitate this policy. Other work has used the Q values. Here, we want to use all the information in the tree because we have a very limited number of tree queries. And so we do a very simple weighted visit count by the Q values. What this means is, intuitively, we have our visit count distribution, which is what the tree search focused on, and we weigh that by the Q value distribution, which is the values that it found. To show you some results here for the rock sample problem, if we just used Q values or if we just use visit counts, this performs worse than if we use a combination of the two. And again, the important part is we want to use all available information in the search tree, given that we have a limited number of queries. So the experiments that we run for this particular section are robot localization. This is the light dark problem in the POMDP literature. Robot exploration, which is the rock sample problem, and then critical mineral exploration. And what we show when we compare against several state-of-the-art POMDP solvers, we can see that we generalize pretty well across the board here. But what's important here is these solvers are with and without heuristics for each of these problems. So these are handcrafted heuristics that require some domain knowledge or a lot of compute to generate. If we then compare BetaZero against these when they do not use heuristics, we can see that because BetaZero is learning a heuristic during learning of the policy, this is where it outperforms significantly across the board. To show you some results from a real-world POMDP, which is the critical mineral exploration problem. Previous work used POMC-POW with heavy reliance on heuristics, where there were heuristics for action selection, which would select actions that have high value and high uncertainty, and value estimation heuristics, where we'd estimate the value based on expected extraction return. So you can see how a neural network might be able to replace these two heuristics. So to explain the results I'm about to show, this plot will show you the uncertainty in the belief as that bright color on the bottom, as well as the probability of selecting one of those drill actions as a bar here. And this is actually showing the results from POMC-POW without using heuristics for about 1 million total simulations. If we compare this to BetaZero with the comparable number of simulations, but it's allowed to learn offline with a smaller number of online simulations, we can see that it's picking actions that have high uncertainty and high value, which is what the heuristics showed from previous work. So the insight from this section is that we can learn from offline experience to reduce online planning horizons, and we can replace expert heuristics with comparable learned heuristics in the process. The last thing I'll show from BetaZero is on the light dark problem, which is really nice because it's a one-dimensional state. This means that if we just have a mean and standard deviation for our belief, then this is a two-dimensional belief space. So we can actually plot the value network and the policy network itself, and then compare this to an approximately optimal value in policy. And qualitatively, we can see that BetaZero is learning an approximately optimal value in policy function. Of course, with any algorithm, there are limitations. For this particular case, we assume known models of the transitions, the rewards, and the observations, which is standard in POMDP planning, but this may limit its applicability to, say, partially observable reinforcement learning problems. We do employ a simplified belief representation that worked well for the problems we study, but this may not scale well to highly non-Gaussian problems. Yet I mentioned several pieces of research that could easily extend this work to those types of problems. This does require a lot of compute to train, yet this is easily parallelizable over CPUs and GPUs, so this can scale well to larger and larger real-world problems. And what's more important for my particular research is that For safety problems, if we want to reach some target level of safety through learning a policy from this method, it requires us to tune the reward function, which is standard for POMDP solvers, which can often be computationally expensive and sometimes somewhat uninterpretable for what those values of the reward function actually mean. So this leads me nicely to my third contribution, which is now that we can plan over long horizons, how do we ensure safety? So this is work that was published last year in the International Joint Conference on Artificial Intelligence. So to remind you what the formulation for solving a POMDP is we want to find a policy pi that maximizes this value over some initial belief. For a chance-constrained POMDP, which is a safety version, we want to still find a policy that maximizes our value, so we have some reward we're trying to maximize. But this is subject to the constraint that the failure probability of the policy is less than or equal to some threshold delta. So we can directly encode what is our desired failure probability of the system, say, fail less than 1% of the time. Existing work on safe planning include applying dual methods or Lagrangian methods, applying linear programming approaches, which often don't scale well to high dimensional state spaces, and also pruning methods, which require you to online run large tree searches and then prune out unsafe branches, again, in the online setting, which might be expensive for particular applications of these types of safe planning problems. So a recent survey identified a need for scalable chance-constrained POMDP approaches to solve these long horizon problems. To show you an example of how this doesn't scale well is for dual methods, you often have to tune a Lagrange multiplier. And the naive way to do it would be to just reframe your reward function. So now you apply some cost to these failure states. And in this case, you could tune this variable lambda. And you would want to find a policy that's on this Pareto front that is on the left side of this failure region. So we have some desired chance constraint, so some desired failure probability. We were on this side, and we also maximize our returns. But what we really want to do is plan directly with this chance constraint itself. So our goal would be to say, plan once to get this desired policy that's shown here, as opposed to having to tune the reward function to then get the behavior that we want. The algorithm that we introduced to address this is called delta MCTS. It extends Monte Carlo tree search to an adaptive safety constraint domain. The idea is we have your standard 4 stages of MCTS. Here, we now have a chance-constrained criteria where we balance selecting actions based on exploration and exploitation, now subject to our failure probability is less than or equal to some threshold delta. And I'll get back to this in a moment. We can then expand by taking that action, get a next belief, reward, and failure probability. We can simulate that forward through some value estimation and estimation of our failure probability for the next belief, and then back propagate the Q value and failure probability F value up the tree. And then we introduce a 5th stage called adaptation that addresses an important piece, which is our target level of safety, delta zero, may be too conservative. So if we say select actions that balance out exploration, exploitation, but are subject to failure probability being below some threshold, in our search tree, we may not have any actions that satisfy this constraint. So then we have no way to select actions that maximize returns. And so the way we fix this is by updating an estimate for the target threshold, delta B, for each belief node using a technique called adaptive conformal inference, which is really just this update function shown here. Adaptive conformal inference, it's a distribution-free sequential calibration method that guarantees valid coverage with high probability in online settings. So this is a perfect use case for our particular problem. Intuitively, what this means is that if we take that update function and break it down into the 2 cases, if our observed failure probability in the tree, this is that F value, is greater than the threshold over the belief, then we will increase that threshold. This allows for more risk in future actions, meaning there weren't any actions that satisfy it, so we want to widen the risk to try to maximize our returns within that regime. Otherwise, if our failure probability is less than or equal to our threshold delta, then we decrease the risk, allowing for safer actions in the future so we can tighten the bound. And of course, we upper bound this by our target level of safety so that we don't over-conservatively reduce our safety at the expense of returns. So now the question is, given delta MCTS, how do we efficiently plan using these safety constraints over long horizons? This may look familiar. We can actually just extend BetaZero to chance-constrained problems. And here now, instead of just estimating value at the leaf node, we can estimate that failure probability. What this looks like is an algorithm we introduced called ConstrainedZero, which is just this natural extension to BetaZero, where the differences are shown in red here, where we input our belief to a neural network surrogate, we predict the policy, which is the probability distribution over actions, the value, as mentioned before, and now a third head of the network, which is the failure probability. We can use this in a very similar offline policy iteration fashion, where we start from initial network, we run n parallel now delta MCTS simulations to evaluate that policy. Here showing the 5 stages I just mentioned, where the neural network is now used in these cases in red, where we can estimate the future failure probability through this addition of the failure head of the network. We can then collect a bunch of data from these runs. The only difference is now we have a failure event indicator to train that third head of the neural network. We can then improve the policy by retraining given the new data, and then repeat this process through a policy iteration loop as before. So now that we have an offline surrogate, we can then, just as before, use this online to safely plan. And the insight is that if we learn a failure probability surrogate offline, then we can plan safely online with adaptive constraints, where the key idea is that if we have a good surrogate for where we fail, then we can plan safely. The experiments we run include a safety version of the robot localization problem, aircraft collision avoidance, and safe carbon capture and storage. The results I'm showing here are ablations given the components of the algorithm that we introduce, and we can see that ConstrainedZero achieves the highest returns within the desired failure probability for each of these problems, where yes, there are cases that might have, say, higher returns, but at the expense of outside of the failure probability window. What this means is we can actually solve for that desired policy, as I showed you before, which was actually the ConstrainedZero policy that we learned. In this case, we don't have to tune each of these BetaZero policies. We can directly encode our safety constraint when we learn a policy. To show you some qualitative results, this is the aircraft collision avoidance problem, where this is showing just some belief slice. And now we look at the policy output of the neural network, where you can see where we would climb and descend from a level intruder. We can see the value estimate, which this would show you areas in which you alert or you reverse. And then also you can look at, say, the failure probability estimate given an individual belief. What this is useful for is you can use this neural network surrogate for further safety analysis. One thing that I want to note is that we're robust to the adaptive conformal inference step size. So that's this eta parameter here that tells you how reactive you are to changes in this safety threshold. What this looks like is that if we sweep the eta parameters, which are these colored lines, we can see that we eventually will converge to desired level of safety at the expense of early returns that then would eventually converge to the desired approximately Pareto optimal policy. So empirically, this is what we see, which balances desired safety with the maximization of utility. Lastly, I want to show you that ConstrainedZero and delta MCTS can also be applied to chance-constrained MDPs, not just chance-constrained POMDPs. What this means is, for an example, say the wildfire resource allocation problem, where we can take actions of aerial water drops. There's some fuel, which is the state of the world, and our failure probability is a threshold on the fire affecting the populated areas, in this case, in the bottom left of this problem. To show you what the trained policy learns is here we have the strips of water drops, and the bottom left is a populated area. After training the policy with ConstrainedZero, we see that the behavior that it learns is actually this indirect attack. So this is common in wildfire resource incident management, where you don't attack the fire directly, you actually build walls around areas that you want to save, because the fire is going to spread faster than the resources can actually extinguish it. So this is some cool behavior that we see emerge from just applying a constraint on the populated area. Of course, limitations of this work include, just as BetaZero, it does require a lot of compute, but this can be easily parallelized and scaled to larger and larger real-world problems just with more compute. It does not provide safety guarantees due to planning with these approximations that are quite large, and also that neural networks are hard to verify and can often be uninterpretable. This leads nicely to the final contribution of this work, which is, given a safe policy that we just learned, how do we validate its safety? So this is work I did in collaboration with X-Wing a couple of summers ago that was published last year in the Journal of Aerospace Information Systems. So to set up the problem, X-Wing is a fully autonomous cargo aircraft company, now part of Joby Aviation, that can fly gate-to-gate fully autonomously. And because it's an autonomous aircraft, there's a lot of components of the system that are safety critical. And the way we want to study this is you can study as a full system end to end, but in our case, we want to study the specific safety critical component, which is a runway detector when the aircraft is on an approach to land. So the runway detector, as you can see here, will try to get bounding boxes of the runway and use this as a way to localize, given, say, a GPS or INS feed, and use the camera feed as additional information in order to localize the aircraft. We could fly a bunch of flight tests to test this, but what we really want to do is to test this in simulation. Doing it in simulation allows us to test, say, nominal runway conditions, We can also test off-nominal runway conditions, say less frequent weather conditions, as well as potentially dangerous to fly conditions. The technique we apply to this work is called safety validation. Safety validation has three primary tasks. The first task is called falsification, which just says, can I find an input that leads to any failure? So it's just find any old failure. Then the next task, which is increasingly difficult, is most likely failure analysis, which is can I find the input that leads to the most likely failure, not just any old failure, but a very likely failure. And then finally, which is the most difficult, is failure probability estimation, which says, can I find a distribution of failures or a way to estimate the failure probability over its entire operating domain? This work focuses on failure probability estimation. And what that means is if we focus on this, we actually get the other two for free, which is really nice. But the challenges here are that we want to validate a black box system. So we just pass in inputs and get outputs from the system, as well as we want to efficiently estimate the failure probability without having to run, say, hundreds of thousands or millions of data points to get a good estimate. So to give you an example for the runway detector, we have a black box policy. In this case, it's just some neural network. We pass in inputs, which could be a photo of the runway, and then we get an output that's just a Boolean that says true or false, did this lead to a failure? We can then use those outputs to fit a probabilistic surrogate model where each of these points is from some parametric operational space, where say we have glide slope, which is the angle in which you're coming to on an approach to land, as well as distance to runway, which is a proxy for when the system would be active. What this means is that this particular point shown here in green is associated with this particular glide slope, angle, and distance to runway. And this was a success, so we actually detected the runway. And this particular box here is a failure for this particular glide slope and distance to runway. We can use a probabilistic surrogate model or a Gaussian process as a way to predict the probability of failure for any one of these points in this space. What's nice about a Gaussian process is this also gives us some uncertainty in that prediction, so we can use that as a way to then pick new points in this space. We apply a logistic transformation to actually achieve this, which I'll save for another time. But the key idea is that if we reframe safety validation as a Bayesian optimization problem, we can then solve this pretty efficiently. The next question is, how do we select new points to then refit this surrogate model to get a better understanding of where we fail in this space? So for Bayesian optimization, there are these things called acquisition functions, which acquire new points in order for you to then run the expensive black box policy. We introduced 3 new acquisition functions and call this whole process Bayesian safety validation. So the first acquisition function is called uncertainty exploration. So the key idea is that we want to explore areas with high uncertainty to both find failures and provide coverage of the space. So if this is our surrogate model where each of those squares is points that we actually have already evaluated, we can see that if we look at the uncertainty in this space, the dark areas means we have low uncertainty. So we're pretty confident about those areas. But the high yellow colors are where we have high uncertainty. So we want to pick points that maximize that uncertainty, which would be here. The next acquisition function is called boundary refinement, where the key idea is we want to refine failure boundaries as a way to better characterize failure regions, which we can arrive analytically based on the logistic transformation we developed for this Gaussian process. If we then define this failure boundary, we can see that we want to pick points on that failure boundary that could be weighed by your operational model to first pick more likely points on the boundary, and then you could spread out over time. And then finally, failure region sampling, which the key idea is to sample from the theoretically optimal proposal distribution to refine likely failure regions, where the theoretically optimal proposal distribution is in fact just the failure distribution. And here we can get a surrogate for that failure distribution to sample from that to get more failures. So with all 3 of these acquisition functions, we can then get 3 new points to input into our black box policy. We get a new output that says out of those 3, which ones failed, and refit our surrogate model. Once we converge to a surrogate model, we can then use importance sampling as a way to efficiently estimate the failure probability. We can either use Monte Carlo integration over this efficient surrogate to estimate this over the entire space, or we can use things like self-normalized importance sampling to do this more efficiently. So some results for this particular approach. First, we test on some toy examples. What this means is that we actually have access to the true failure probability, so we can see exactly how our estimate compares to the truth. Here, this is showing the failure region for 2D problems compared to what the surrogate model learned. And you can see, at least qualitatively, these match very closely. But what's important is we then compare this quantitatively against different sampling schemes, meaning, say, we sample uniformly random over this space to pick new points, or we can use, say, space filling algorithms like Sobel sequence sampling or Latin hypercube sampling. How does this compare to Bayesian safety validation? The important one that we see here is that Bayesian safety validation consistently gets less than 1% error in the probability of failure, meaning it's getting a very good estimate of the failure probability, while also having high likely failures. So it's finding really useful failures and a high failure rate, meaning we have a lot of examples of failures that we can then go try to fix. To show you this in action for the runway detection system, you'll see here that the 3 points will be fit from the surrogate, where each of these iterations is sampling points from each of these acquisition functions. Uncertainty exploration is going to bounce around this space to try to tamp down that uncertainty. Boundary refinement is going to start first at likely boundaries and then move its way out towards the edges. And then failure region sampling is going to just do that, is sample from that failure region. What I can also show you is this, but with the input to the actual runway detection system. This is cool to see because you can actually see you're jumping around this space on an approach to land. So for uncertainty exploration, you see this is pretty jittery because it's going around this entire space here. The boundary refinement is trying to just refine right where you fail to get a better understanding of the actual boundary. And failure region sampling is going to try to sample more failures. So this is pretty red throughout this process. After we've converged and we have a surrogate model that we're happy with, we can then look at things like what is the failure rate, meaning how many failures did we actually sample from out of, say, in this case, we have 1,000 data points. What is the most likely failure? What is the estimate in the probability of failure? Of course, we don't have access to truth, but we can get an estimate. In this case, we can see that we have about 6 times 10 to the minus 3 for probability of failure, meaning that we ran about 1,000 samples. And what that means is if we then just did Monte Carlo estimation, out of those 1,000 samples, we would only expect 6 of them to be failures. But in our case, we have almost 600 failures. This distribution shows the likelihood, the log likelihood of the failures. Because it's right skewed, that means these are more important failures. So they're not just any old failures, but these are actually important failures. Lastly, what we can do is then see things like the most likely failure, which is actually this little island right there, and start there to triage, trying to resolve these particular failures. We want to start from the most likely failure and go down. To step back as a reminder, safety validation is just one piece of the safety puzzle. So here we introduce a method to efficiently estimate failure probability. This has been used to augment the FAA certification for X-Wing, where it's applied to this runway detector that uses a neural network. Other things you could do is to validate the simulator itself using sim-to-real techniques. In this case, say, take flight test images and use a style transfer to go from an image like this and map it onto what you see in simulation. And again, Bayesian safety validation is just one component used to validate these safety critical systems before they're deployed. So to take a step back further, I've introduced 4 main contributions of my thesis here: ways to plan more efficiently for real world problems, and then ways to apply safety techniques in order to plan safely, and then to validate the safety of those plans. Of course, no research is ever completed. Some future work could look into applying neural network verification techniques in order to provide safety guarantees. This could, say, apply reachability methods in order to do so. We could also look into interpretable surrogate models that would trade off interpretability with performance. So things like neural networks are really hard to interpret from a human's perspective, but say a decision tree, which is just a simple decision tree, may be easier for humans to understand, but at the expense of performance potentially. And then finally, we could look at offline chance constrained methods in order to learn offline policies with safety guarantees baked in. All this work, I was lucky enough to be able to publish during my time as a grad student, where the ones in white are the ones presented here today. I'm a huge proponent of open source code. Everything you saw here today is open source. Most of it is written in Julia. Towards the end, I strayed from the path of righteousness and did something in Python. But of course, everything else is in my beloved Julia. And now I'm happy to take any questions. Thank you for listening.